Hello, today we're going to be looking at section 11.2 and a little bit of section 11.4, which is about vectors and lines in space. And just for a little fun, you might recall this quote from this week. Our goals for today, that we can find the component form and magnitude of a vector, we can find the dot product of two vectors, find the angle between two vectors, determine if two vectors are orthogonal, find a vector that's orthogonal to a given vector, determine if two vectors are parallel, find the terminal point of a vector, and find parametric and symmetric equations for lines in space. Let's start with some definitions and formulas. So you might recall that we looked at 2D vectors previously this year. So now we want to extend that to three-dimensional space because many physical forces and velocities are not confined to a two-dimensional plane, but occur in three-dimensional space. In space, vectors are denoted by ordered triples. Recall that vector notation we saw several types of vector notation. The one that you're going to be seeing the most in this chapter is going to have the lowercase boldface letters, and then the component form in angle brackets. So V sub 1 represents your x component, V sub 2 represents your y component, and V sub 3 represents the z component for your vector. If the directed line segment from point P to point Q form a vector, then the component form uses this formula, but basically it's how far did you go in the x direction, comma, how far did you go in the y direction, comma, how far you went in the z direction from P to get to Q. You can find that by subtracting each of the Q components minus the P components, or you can just think about how far did I go from P to Q for each direction, x, y, and z. Magnitude, you might recall this formula. We've just got an additional component here. So magnitude is denoted with the double bars. It's equal to the square root of the sum of each component squared. So the square root of V sub 1 squared plus V sub 2 squared plus V sub 3 squared. To find a unit vector, U in the direction of V, you take the components of vector V and you divide it by the magnitude. So for our first example, we're going to find the component form and magnitude of vector V that has an initial point at 3, 4, 2, and a terminal point of 3, 6, 4. And then we'll find a unit vector U in the direction of V. So to find our component form, we're going to figure out how far we went in the X, Y, and Z directions. You can substitute that into these formulas if that helps you. So Q is my terminal point, P is my initial point. So Q sub 1 is 3 minus P sub 1 is also 3. Q sub 2, my y component of my Q point, 6, minus my y component of my first point, 4, comma, my z component of my first point, or my terminal point, 4, minus the z component coordinate of the initial point, 2. Well, 3 minus 3 is 0. 6 minus 4 is 2, and 4 minus 2 is also 2. So our vector has components of 0, 2, 2. To find our magnitude, we're just going to substitute each of these components into our magnitude formula. So 0 squared plus 2 squared plus another 2 squared. Well, 0 squared is 0, 2 squared is 4, 2 squared is 4. So 0 plus 4 is the square root of 8. And if you simplify the square root of 8, that is the same as 2 root 2. Please make sure you're leaving your magnitudes in radical form, simplified radical form, and not using decimals. For our unit vector, we take each component of our vector and we divide it by our magnitude. So our x component 0 divided by our magnitude of 2 root 2, comma, our y component of 2 divided by our magnitude 2 root 2 over 2. And then our z component 2 also divided by 2 root 2 over 2. Well, 0 divided by anything is 0. Here, 2 divided by 2 is 1, so we have 1 over root 2. Again, 1 over root 2. But recall that we don't like radicals in the denominator. That's not considered simplified. So if you rationalize, if you multiply both the y component and the z component by square root 2 over square root 2, we end up with 0, comma, root 2 over 2, comma, root 2 over 2 for our unit vector. So recall that a unit vector is a vector with a magnitude of 1, but this would be going in the same direction as our original vector v. All right, some more formulas for us. The dot product of two vectors, if vector u has components of u1, comma, u2, comma, u3, and vector v has components of v sub 1, v sub 2, and v sub 3, the dot product is given by the formula. Now this is read u dot v. Okay, so I know it looks like your traditional multiplication symbol, but when we read this out loud, it says u dot v. Okay, is u sub 1 times v sub 1 plus u sub 2 times v sub 2 plus u sub 3 times v sub 3. So you multiply your x components together, you multiply your y components together, you multiply your z components together, and then you add those three numbers together. So you're going to get a single number, a scalar quantity from the dot product. Okay. Our next formula, if theta is the angle between two non-zero vectors, u and v, okay, so this angle here, then the cosine of that angle is equal to u dot v divided by the magnitude of u times the magnitude of v. Note though that the angle between a zero vector and another vector would be undefined, because a zero vector would give us a magnitude of 0, and we cannot divide by 0. That is undefined. All right, so example 2, we're going to find the dot product of vector u with components of -1, 3, and 5, and vector v with components of 0, 4, and -2. So there's our formula again. If we substitute in our components, okay, u sub 1 is -1, v sub 1 is 0, plus u sub 2 is 3, v sub 2 is 4, plus u sub 3 is 5, and v sub 3 is -2. -1 times 0 is 0. 3 times 4 is 12. 5 times -2 is -10. So we have 0 plus 12 plus -10, which gives us a dot product of 2. For example 3, we're going to find the angle in degrees between the vector u with components of 4, -1, and 3, and vector v having components of 0, 1, and 5. To do this, we need to find our dot product and then the magnitude of vector u and the magnitude of vector v. So for our dot product, 4 times 0 plus -1 times 1 plus 3 times 5, well, 4 times 0 is 0, -1 times 1 is -1, 3 times 5 is 15, 0 plus -1 plus 15 is 14. We find the magnitude of vector u, so square each component of the vector and then add those together, and then take the square root. So we have 4 squared plus -1 squared plus 3 squared. 4 squared is 16, -1 squared is +1, 3 squared is 9, so 16 plus 1 plus 9 is 26, so we end up with the square root of 26. For vector v, we find its magnitude, so 0 squared plus 1 squared plus 5 squared, well, 0 squared is 1, 0 squared is 0, got ahead of myself there, 1 squared is 1, and 5 squared is 25. 0 plus 1 plus 25 gives us 26. So the magnitude of vector v is also the square root of 26. Now, it won't always work out that the two vectors have the same magnitude. It just happened to happen in this case. Now that we have those things, we can use our formula for finding the angle. So recall that cosine of theta is equal to u dot v divided by the magnitude of u times the magnitude of v. So if we want to get just theta, we'd have to do inverse cosine of that expression. So if we substitute in our dot product and our magnitudes, we get theta is equal to the inverse cosine of 14 over the square root of 26 times the square root of 26. Notice that our direction said that we're going to find the angle in degrees, so make sure your calculator is in degree mode. And if you type in the inverse cosine of 14 over square root 26 times square root 26, you get that theta is about 57.42 degrees. Next up, orthogonal and parallel vectors. Two vectors are orthogonal, which is kind of another word for perpendicular, if their dot product is 0. Now, orthogonal, if you go on to take some future math classes, it's kind of considered a better word than perpendicular because it applies to a lot more situations. Perpendicular, we tend to just talk about in regards to lines and planes, things in basically two-dimensional space. But we can talk about things being orthogonal like vectors, but also functions can be orthogonal. And so orthogonal is a better descriptive term that leads into future math classes and into things involving higher dimensions. Okay, but for now, all you need to know is two vectors are orthogonal if their dot product is 0. Two vectors are parallel if one vector is a scalar multiple of the other. So vector u is equal to some constant times vector v. That would mean those two vectors are parallel. So for example, in this figure, vectors u, v, and w are parallel because you can get vector u by multiplying vector v by 2. You can get vector w by making it be the opposite of vector v. So if you can take a vector and multiply it by a constant to get another vector, then they are parallel. So example 4, we're going to find the value of c that makes the two vectors orthogonal. So vector u, we have -8, 1, c plus 10. Vector v is 3, -4, 7. Now we know in order for them to be orthogonal, their dot product has to be 0. So we're going to set this up as an equation with the dot product and set it equal to 0. Okay, so for our dot product, you multiply your x components, multiply your y components, multiply your z components, add them together, and then in the case of this equation, I'm going to set that equal to 0. So -8 times 3 plus 1 times -4 plus c plus 10 times 7 needs to equal 0. Well, -8 times 3 is -24. 1 times -4 is -4. C plus 10 times 7, make sure you distribute, gives us 7c plus 70. And we need that to equal 0 for these to be orthogonal. We do a little bit of simplifying. Now we have 7c is equal to 42. You could subtract 42 from both sides to get 7c is equal to -42. And if you divide by 7, c is equal to -6. Example 5, we're going to determine if each vector is parallel to vector w, if vector w has an initial point of 1, 2, 3, and a terminal point of 9, 8, -7. So when and the three vectors we're going to compare that to are a vector with an x component of -4, a y component of -3, and a z component of 5. Then we're going to look at the vector 10, 8, -8. And then we'll look at a vector with components of 16, 12, and 20. So the first thing we need to do, because we're just given the points on vector w, is to find its component form. So either you can use the formula or you can just think from initial to terminal. So from 1 to 9, we went +8 spaces. From 2 to 8, we went +6 spaces. From 3 to -7, we went -10 spaces. So here's our component form of vector w. Now we want to determine if there's a scalar, if there's a constant that we can multiply w by to get each of these vectors, okay? To be parallel, if you can multiply by a constant to get the other vectors, we know they're parallel. Okay? Now some of you are going to be able to look at these and figure it out mentally. But if not, you can actually set up ratios to determine this, okay? It turns out that the vector here in part A is parallel, and we know that if you divide each of the components, so -4 divided by 8 is -1/2, -3 divided by 6 is also -1/2, and 5 divided by -10 again gives us -1/2. So if we were to multiply vector w by -1/2, we would get the components in this vector here, which means they're parallel. And that constant c is -1/2. B is not parallel. Okay, if you were to set up the ratios, 10 divided by 8 is 5/4, 8 divided by 6 is 4/3, -8 divided by -10 is 4/5. There is not a constant that you could multiply every component of vector w by in order to get this vector here. So not parallel. C is also not parallel, and you might be tempted if you weren't paying attention to think that they are. Okay, because 16 divided by 8 is 2, 12 divided by 6 is 2, 20 divided by -10, ooh, that's -2. So watch out, because sometimes two of the components can be multiplied by the same constant, but the third component can't be, okay? So make sure that that in order for them to be parallel, you find a constant that multiplies by all three components to get the new vector in order for them to be parallel. All right. Next up is a little bit from section 11.4, looking at lines in space. So back in your geometry days, we looked at lines on a plane in 2D. Now we're going to take a look at lines in three-dimensional space. So in a plane, we use the slope to determine the equation of a line. And you learned lots of ways for writing the equation of a line. Slope-intercept form, point-slope form, standard form. However, working in three-dimensional space, it's much more convenient to use vectors to determine the equation of a line. So if you have a line L that goes through a point P with coordinates x1, y1, z1, that is parallel to vector V with components of A, B, and C. Then vector V is the direction vector for the line, and A, B, and C are the direction numbers. And line L will consist of all the points Q such that from the vector from P to Q is parallel to vector V. Continuing with that, well, if vector PQ is parallel to V, then that means there is a scalar, a constant, that we can multiply vector V by in order to get vector PQ. To find our component form for vector PQ, well, we would subtract our terminal minus our initial coordinates for both x, y, and z. So x minus x1, y minus y1, z minus z sub 1. Or if you think about it as being a multiple of vector v, okay, where t is that scalar, that constant, you would do t times a, t times b, t times c, which we already saw. All right, so a line L that's parallel to vector v with components of a, b, and c that passes through the point P with coordinates of x1, y1, z1 is represented by the parametric equations x equals x sub 1 plus at, y equals y sub 1 plus bt, and z is equal to z sub 1 plus c times t. So notice that in these our parameter is t. When a, b, and c are all non-zero, you can eliminate that parameter to obtain the symmetric equations of a line. So if you recall back to chapter 10 when we were working with parametric equations and we were eliminating parameters, we've got a little tie back into that here in three-dimensional lines. Okay. So basically what you do is you solve each of these equations, your parametric equations, to get t by itself, and then you set them equal to each other, and that's how we get these symmetric equations. X minus x sub 1 over a is equal to y minus y sub 1 over b, which is equal to z minus z sub 1 over c. So example 6, we're going to find the parametric and symmetric equations of a line L that passes through the points passes through the point 3, 2, 1, and is parallel to vector v with components of -1, 3, and 5. So here this point gives us our x sub 1, our y sub 1, and our z sub 1. We're given the vector, so we have our direction numbers a, b, and c. So let's start with our parametric equations. I just reminded you of what those look like. So we're just going to substitute our values for x1, y1, z1 here, and our values for a, b, and c here. So x is equal to x sub 1, which is 3, plus a, -1 times t. So we can just write that as 3 minus 1t or 3 minus t. Y is equal to y sub 1, which is 2, plus b, 3 times t. So y equals 2 plus 3t. And z equals z sub 1, which is 1, plus c is 5t. So z equals 1 plus 5t. Those are our parametric equations. For our symmetric equations, and reminding you what that looks like, we're going to substitute in our x1, y1, z1, and our a, b, and c. And we get x minus 3 over negative 1 is equal to y minus 2 over 3, which is equal to z minus 1 over 5. And there are symmetric equations for this line. All right, one last example for you. This time we're going to find the parametric and symmetric equations of the line that passes through the points 1, 4, negative 2, and 4, 0, 3. When you're given 2 points like this and they're not labeled, assume that the first point is P and the second point is the Q. And point P gives you your x1, y1, z1. So the first thing we need to do is find the component form of the vector from P to Q. So again, from your initial to your terminal, how far did you go? Or you can subtract terminal minus initial to get each of your components, whichever way you like. Okay, but from 1 to 4, we went 3 spaces. From 4 to 0, we went negative 4 spaces. And from negative 2 to 3, we went 5 spaces. So here's our component form for our vector, which gives us our values for A, B, and C. So now that we have our x1, y1, z1, and our A, B, and C, we can write our parametric and our symmetric equations. So our parametric equation, x equals x sub 1, which is 1, plus a times t, so 3 times t. For y sub 1 is 4, plus b is negative 4, so 4 minus 4t. And for z sub 1 is negative 2, plus c is 5, so negative 2 plus 5t is equal to z. And here we have our parametric equations. For our symmetric equations, x minus x sub 1 is 1 over a is 3 equals y minus y sub 1 is 4 over b is negative 4 equals z plus, well, since it's z minus z sub 1, z minus negative 2 gives us positive 2 over c is 5. And there's our symmetric equation for this line. Here's your assignment. Please reach out if you need any assistance. Good luck.